Hello, everyone. I wish to talk about how to apply Squeeze theorem. You just had a quiz where there were two questions that you need to apply Squeeze theorem. And first of all, let's understand what Squeeze theorem, right? Squeeze theorem says if G is between F and H, when X is near A, except possibly at A. Okay, we must understand this phrase. What does this mean? It means that F, G, H, right? F is lower than G, G is lower than H. But this is only happening in a small neighborhood of A, right? Like in this picture, right? The green is the H, G is the pink, and the blue is in the bottom. And this doesn't mean they are in this relationship all the time, right? If you draw a vertical line, okay? On the vertical line, you can see the green H is above the pink, right? And the pink is above the blue. And that is true in this neighborhood of A, okay? And it's a small neighborhood of A, so near A, okay? So let me show you where's A, right? Of course, A is right here. Let me make it just a little smaller so you can see everything. Hold on, let me redo this. Okay, so F is below H, okay? F is below H, this is F, below G. G is below H. And G is squeezed in between two other functions. One is blue and one is green, but this is only happening in the neighborhood of A. How big is that neighborhood? Well, it looks like this much, okay, in this neighborhood of A. And possibly, except possibly at A. So at point A, it may be a different story, but because in limit, we don't consider the value of the functions at A, so whether these three functions are all defined or not defined, or one of them is defined at A, or all of them are defined at A, it wouldn't matter to us. And if you keep observing, you can see outside the neighborhood. Outside the neighborhood here, G is actually above H. So that is not true. This relationship is not true, but it wouldn't matter. Only if this relationship is true in a small neighborhood of A. Okay, so this is the first condition. So when we apply the theorem, we need to understand what are the conditions we must apply we must check in order to apply the conclusion in that theorem. Okay? Now, when we apply certain theorem, we have to check all the conditions required by the theorem. So that's the first condition. And the second condition, okay, so the first condition was here, okay, so I'm going to write it down. So squeeze theorem, when you are taking notes, okay, what should you be doing? You squeeze the theorem has a number of conditions or premises that needs to be satisfied before we can use the conclusion. Okay, listen to me carefully. We apply certain theorem, we have to satisfy all the conditions that spell out by the theorem. Otherwise, we cannot apply the conclusion. So to understand these conditions, and you need to identify what are the conditions. So the first one is, right? So the premise, okay? The premise, there are multiple premises, okay? The more than one condition. The first one is f of x less than or equals to g of x less than or equals to h of x. Okay, and this condition is true when x is near A, except possibly at A itself. So this condition must be observed completely, including all these small details. Secondly, okay, this line actually is spelling out how many conditions? Actually, 1, 2, 3. The first one is saying, right, F is the one below, right, beneath. Okay, so the limit of F when X is approaching A is L. And limit of G, I'm sorry, the limit of H, the limit of H, right, is also exists and as approaching L. Okay, so both have limit and their limit are the same. That's what it's saying. Okay, so that's why the 3 condition. This limit exists. Okay, look at the 3 condition. This limit exists, it's L. And this limit exists, it's L, right? Or this limit exists and that limit exists and they are the same. So that's the 3 conditions. Okay, or you can write it down whichever way you want, but these are the conditions to be checked. If this is true, if these 2 major conditions are true, then limit of G, which is the one in the middle, okay, which is the one in the middle, limit as X approaching A, G of X would be the same as L. So that's what the squeeze theorem is saying. So when we apply the squeeze theorem, right, when we apply the squeeze theorem, say the, number 4, right, number 4 says if, right, if 4x minus 9 less than or equals to F and less than or equals to x squared minus 4x plus 7 for x is greater than or equals to 0. So this is a given. This is a given. If you compare the first condition, right? It says, F is beneath G. What is F? F is 4x minus 9. What is H? H is is x squared minus 4x plus 7. And what is F, right? What is G in this situation? Well, that's our F. We actually don't know. Okay? Some of you took 4x minus 9 as F, or some of you took x squared minus 4x plus 7, at least in your writing at F. Those are horrible, terrible mistakes because we don't know what F is. Okay? And this is true for x is greater than equals to 0. What does that mean? If we just take a picture, right? You don't need, well, to do this question, you don't need to see, you don't need a graph. But here, as I'm explaining, okay, what is the function below? What is the function above? Okay, so I'm going to use the color tone for these pictures. 4x minus 9. Okay, so all of these are just, things you analyze. You don't have to show these work, but you should know it, right? 4x minus 9, that is the curve, that is the line, right? It's a straight line. And what color do we want it to be? I'm going to make a correspondence to the color, which is the blue, right? The color blue. So I'm going to change that to the color blue. Blue color. Right here. Okay. Greater than equal to 0. So I'm going to make some more adjustment to this picture later. Okay. Then I'm going to graph the function on the right. Okay. Which is x squared minus 4x plus 7. And this is green. Okay, this is green. Right? This is green. But we only look at for x greater than equal to 0. For x greater than equal to 0, so I'm going to make a little adjustment. Okay, so x is going to be from -1 to say 10. And this one, make it -20. And higher up, I'm going to make it 20 to see how that works. Okay. You see the picture? You see the picture, right? You see the picture right here. Okay, on this picture, F is in between. Do we know what F is? We don't. Okay, so some of the mistakes I saw. Okay, some of you took 4x minus 9 for F. Okay, so we need to understand. Okay, some of you took f of x, at least in your writing, it reflected that you took f of x as 4x minus 9, whether it's a habitual or it's just a careless mistake. Or you take, not everything is called F, right? Once F is given, you cannot just use it everywhere else. And some of you use f of x for that function over here. That's not true either. We don't know. We actually don't know what F is. Okay, all of these are mistakes. We don't know what F is. In fact, F is between the two. It could be anything between the two. It could be going this way and squeezed in here and then go down, right? It could be anything. So you cannot assume F is one of the two. One is above, one is below. So that's one mistake, okay? And the other thing is because we know Okay, so we're checking the condition. So the first condition is saying, I mean, in this question, it's just, we didn't give a name for these two, but you can totally give a name for these two, right? I can say the blue one, this is the F in the theorem. The green one is the H in the theorem. And F is the G in the theorem. I hope you guys see the correspondence. But in general, the name wouldn't matter. It's what they are matters. So what do we see in this question is that this relationship is true for x is larger than or equal to 0. So we can safely assume, right? Because the limit of interest is 4, right? Since the limit of interest, okay, the limit of, okay, since this limit, let me write it down this way. Since this limit, right, when x is approaching 4 is our interest. So we will be thinking of in the neighborhood of 4. Since this is our interest, right? Since this is the interest, this is the interested, this is the interest, okay? This is the interest, okay? So when we apply the theorem, we will be seeing, okay, is this condition satisfied in the neighborhood of 4, right? If it is satisfied for all the x greater than equals to 0, and we can certainly apply saying that this is in the neighborhood of 4. Okay, you just have to make the neighborhood small enough, it will be that. So here, when you check the first condition, let's check a condition, right? So the first one, when you check the first condition is saying this, right? And how do you apply that condition? Well, this is F, and this is the 4x minus 9, right? And H is what? H is x squared minus 4x minus 7. When x is near 4. So the first condition, except possibly F of 4, because we really don't know what F is. The first condition is satisfied. Okay? Second condition. The second condition, you need to, well, we need to check the 3 conditions, i.e., we need to check the limit of the function, which is the blue, and we check the limit of the function above. So we have a function below, we have a function above. I think this will be easier to explain. So for F, right, I'm going to check the limit for when x is approaching 4. For the function below, and we're also going to check the limit, right? When x is approaching the same thing on the function above. It will be ideal if you put, it will be best if you put a parentheses. Okay, I found these parentheses are missing, but you really should be putting a parentheses. Okay, now we're checking to see if the second conditions are satisfied. Second condition, of course, includes 3 elements, right? 2 limits, whether the limits are the same. So when x is approaching 4, then this is a polynomial. 4x minus 9 is a polynomial. Therefore, we can substitute. minus 9, and that equals to 7. And the second one is also a polynomial, so we can substitute. Okay, so this is 4, and that is 4. And the limit, once again, is 7. And so these two limits are the same. So if you want to emphasize that very obvious fact, it's even better, right? Which you're quoting the theorem. You're quoting the theorem. If you're quoting the theorem, and that's even better. I said the more you quote, the more points you get. Sometimes quoting the theorem, meaning that you point out the most obvious fact, okay? The function below and the function above. That's function above. And of course, A is 4, and L is 7. So both conditions are checked and they're satisfied. And then we can apply the theorem, okay? So 2 conditions, 1 conclusion. 1 conclusion, and that conclusion, of course, is often in the statement followed by then, if then, okay? So then what do you say? Then you say, by Squeeze theorem, the limit of our interest, this limit, even though we don't know what f is, equals to 7. This is the whole of how to apply a theorem. I hope you guys understand, okay? And a lot of you guys' work is very good, but some of you guys' work needs improvement. And you need to learn the way of writing. You need to learn, and you need to learn how to make the narrative. So you check the condition only when all the conditions are satisfied in the theorem, right? 1, 2, and 1, 2, and then you can apply the conclusion of the theorem. Otherwise, you cannot. Otherwise, you cannot apply that theorem. Okay, so that was the one, you know, on the quiz. And the other one we had is number 6 on the homework. It says prove that the limit, okay, the limit when x is approaching 0. And here we have x raised to the power 4 and cosine of 2 over x equals to 0. In this case, okay, of course, you guys know that we're going to apply the theorem, Squeeze theorem. But in this case, the function below and the function above are not explicitly given. So we don't know what function below this function, and we also don't know what is above it in the neighborhood of 0, in the neighborhood of 0. So this is another situation that you need to create a squeezed situation. How do you create a squeezed situation? Is that you're going to use existing facts, existing truths to create that situation. Okay, so we need to create. So I put a note. Well, you know, we need to create a squeezed situation where only, I would say, near 0, except possibly at 0. Okay, what am I quoting? I'm quoting the first one. Okay, so that's the idea. Okay, and of course you don't need to show this. You don't need to write it down, but I'm just saying, you know, in my thoughts, right? And I suspect Squeeze theorem will do the job. So I'm going to work towards it. But how do you establish that inequality? We're going to use existing fact. So what are the existing fact? Existing fact. We have learned a lot of existing fact in algebra. Okay, one of them is cosine of anything. Cosine of anything is between -1 and +1. That's the range of cosine function. Okay, you learned that in trigonometry. And anything including 2 over x. And then, of course, you would think of the domain. Of course, the domain does not include, okay, the domain here is x not equal to 0. X cannot be 0. That's all. But because we consider the limit as 0, but whether the function is defined as 0 doesn't matter. We don't care. And therefore, if this is true, right? If this is true for anything, if this is true, right? Cosine of anything is between -1 and 1. Certainly, when that anything is 2 over x, it is also between -1 and 1. This is the range of cosine. Range of cosine. Okay, if you want to have further information, if you want to understand why, and you will find a lesson in week 1 on cosine function. So we're using that fact. Okay, so from this fact, right? And we know that x is not equal to 0, x to the power 4 is positive, right? So since x is not a 0, x raised to the power 4 is a positive number. So we're going to multiply this positive number on each side of this inequality. On each side of the inequality, i.e. we're going to multiply by x to the power 4 here. Wait, sorry. We're going to multiply by x to the power 4 over here. Multiply x to the power 4 here, and multiply x raised to the power 4 here. Why can we do that? Well, in your algebra class, you probably have learned that if A is less than B, then A times C is less than B times C, provided that C is positive. Okay? If A is less than B, then A times C is larger than B times C if C is negative. Okay, why is that? Right? Why? Well, any number, right? If A is less than B, if you look at number line, Okay, let's look at the number line. Let's look at the number line. If A is larger than B, I'm sorry, if A is smaller than B, okay? So this is A, and this is B. Let me put an origin. Okay, let me put an origin here. So put a 0 here. Okay, that's 0. If A is less than B, A is smaller than B. A is smaller than B. Okay, then I multiply a positive number for each, right? Say 2 times A is going to be further to the other direction, 2 times B. The first one is easy to understand. The second one, if A is less than B, but we multiply by a negative number, C is negative, right? If I multiply, say I multiply by -1, for example, right? Suppose I multiply by -1 and A is, let me give you some concrete example, okay? A, B, suppose I have over here is 2, over here is 3, right? Now, we know that 2 is less than 3. 2 is less than 3, right? Everybody knows that. But if I multiply both sides by -1, okay? So 2 times -1, and then I'm going to do 3 times -1. Okay, and of course we know this is -2, this is -3. Where is it going to be -2? -2 is going to be here, right? This is going to be -2. And where is it going to be -3? -3 is going to be here, -3. Okay. Oh, I hope I don't create a mess to confuse you. Okay, so -2, -3. So this is -2, and that's -3. Okay, let them to be apart. Okay, so 2 times -1 becomes 2 times -1 becomes -2. 3 times -3, 3 times -1 is -3. So when we do this, -2 is larger than -3. So that's why the directions of inequality will change. Okay, when we multiply by a negative number. So what we used here in our proof is that we multiply by a positive number on each side of the inequality, so the direction will stay the same. Had I multiplied by a -1, it would have to switch directions. Okay, I hope that's clear. Okay, but anyway, so that step, okay, so this step is because x raised to the power 4 is a positive. You multiply by a positive number, and so this property applies. So what do we get? We have just created a squeeze situation. So there's not a given squeeze situation, but we created one. Okay, so now the function of our interest is squeezed in between 2 other functions, one below, one above. One below, one above. But you can graph it if you want, but we're only interested in the neighborhood of 0. Okay, so the first condition, right? What is the first condition in the theorem? The first condition in the theorem is that the interested function is squeezed between the 2, right? And this is true, this is actually true everywhere. Certainly is true in the neighborhood of 0, right? Because from here to the next step, we don't need any additional attachment or conditions. So this is true everywhere. Certainly it is true in the neighborhood of 0. So the first condition is checked. Okay, so this is the first condition is checked. So let me put a note here. You don't have to explicitly say number 1, number 2, but you do need to have that narrative. Okay, so the first condition in the Squeeze theorem is checked. Is true. Is checked and true. And then we're going to check 2 other conditions. What are the 2 other conditions? We're going to check the limit of the function below, and we're going to check the limit of function above, right? So next, we're going to check the limit, right? The limit, right? What are the limit? The function from above and the function from below. Okay, and there are direct substitution because they're polynomials, direct substitution. So the second condition, if you want to, point out the most obvious, go for it, right? And you can say, just like we said in here, right? In a similar situation in Squeeze theorem, let me clean this up. Okay, if you want to point it out, go for it. That is, i.e., right? When x is approaching 0, you just have to put this over here, right? And you're going to put this other one over here. And I hope you understand what I meant. It's equal to 0. So you pointed out directly what is the second condition. Usually this kind of narrative is ideal. So it makes it so easy for the reader to understand what your intention and the related theorem used. Okay? First condition checked, second condition checked, and then you say by Squeeze theorem. Okay, the set limit, which the function is squeezed in between, is 0. And that will be the end of proof. And that's how you prove theorems. That's how you prove theorems. You take each condition explicitly and illustrate to the reader. You do this work because you want the reader to know you understand what you're doing. Okay. So how do you show work for this latter one? Right, I'm going to just trim. I'm going to trim something. I'm going to make some trimming to show you how to prove this one because some of these things are not really necessary. Okay, I put some notes in between. So the work you need to show, right, to prove this limit equals 0, you don't have to tell the reader you're doing that. The reader can tell, right? You can point out the domain, but you don't have to say existing fact, right? You can just say, and this is true, right? You can say for any x, for any real number x, which is a domain, for any real number x, and certainly it's true for x is not equal to 0, for any real number x. Okay, if you want to attach not equal to 0, even though the range for cosine, it can be any real number, and here you can just say for any x, or if you like to say for all, you can use shorthand notation for all x. Okay, whichever x you talk about. Okay, this will be fine. And the next step, right? You multiply x to the power 4. If you could point out x to the power 4 is positive, that would be amazing. Okay. And the next one, okay, it's just you organize just simplify what we did on this step, and it becomes the next one. You don't even have to tell the reader that it's true. The reader can tell usually when you get to this point. Okay, and then you can say and, right? Okay, you can condense it, this limit and that other limit are equal to 0, i.e., right? You pointed out this is, it's okay. If you don't have it, it's fine. By Squeeze Theorem, this is, so it can be just as short as this one. Okay, if you skip this one, if you skip this piece and just go here directly, that'll be fine too. So this piece is optional, but knowing x to the power 4 larger than 0, that's usually considered, obvious. If x is if x is not a 0, x to the power 4 is greater than 0 should be considered obvious. When you pointed out that obvious fact, that will help you. That will help you. Okay, so that can be the proof for number 6. And I hope this gives you sufficient guideline for you to be able to do the rest of them. Okay, and once again, I don't want to make this too long. And thank you for watching. And if you have any questions, please don't hesitate to reach out to me. Thank you for watching.